Then I shall jump right in. So hello, good morning, everyone. Thanks for listening in. I will start with an outline of what I'm going to talk about today. So first, we'll have a short look at the state of automated driving. So what features are currently on the market, what features we can expect in the next few years, and of course also what implications that has for system architectures that we need in automated driving. We will then move on to the main part of my talk. So basically, when it comes to fail operational systems, the challenges that we face in making and designing such architectures and potential solution strategies that we can employ for addressing them. We will then, in the third part, combine all the different solution strategies that I'm going to talk about into one reference architecture, and I'm also going to discuss a bit about what we need in order to make that a reality. And finally, I'm also going to talk a bit about what we are doing at TTTech Auto in order to support efforts to make this reference architecture a reality. Okay, if we think about automated driving, if you go out there shopping for automated driving features, what you can buy currently are, if you're familiar with the SAE levels of automation, up to level 2 features, so-called partial automation. Those are more driving assistance features, so ADAS, than real automated driving. They come in two main flavors. So one of them is more on the safety side. We have stuff like automated emergency braking that makes it a little bit safer. And on the comfort side, where you have stuff that makes boring or repetitive tasks a little bit less taxing, a little bit less annoying. So examples would be here, parking assistance for parallel parking, for example, or on the highway when you're driving for hours, adaptive cruise control. Important to note for these features up to level 2 is that at all points you are still responsible. So you as the driver are still responsible for the vehicle. In case the system fails, you need to be able to take over immediately. So while these features are active, things might be a little more comfortable or a little more safe for you, but they don't fundamentally change how you drive. You're still at all points, you are the driver, you are driving. This will hopefully change quite significantly in the next few years when we expect the first level 3 and level 4 features on the market. Here, the big jump is that, at least temporarily, the vehicle assumes full responsibility for itself. So not only does it do the actual driving, it also monitors itself, whether there is any fault occurring. And if such a fault occurs, it still needs to maintain safety of the vehicle. This allows the driver to temporarily become a passenger, and that actually means that you are then free to do other things. So you gain some quality time while you're driving. Examples are what I'm showing here, for example, a traffic jam pilot or highway pilot systems. In those cases, you are free to read a book, you're free to watch a video, do something else. So you actually gain real quality time out of that. Other examples are, for example, valet parking, where you actually, valet parking, can you still see it? Okay, because my screen is flickering between two views. This is strange. Can you still see the presentation? Okay, good. Hope it's back now. Valet parking, where you can already exit the vehicle and the vehicle parks itself on an unrestricted parking lot. So there also you gain quality time, you can do something else with your life. Still, for level 3 and level 4 features, the fundamental business model of cars doesn't change. So you will still at times need to be able to drive. You still need a driving license, and most of the time you will also own the car that has such a feature. This can be expected to change only when we go further into the future. So once we have mobility as a service, the fabled robotaxi, which is a very desirable feature, where you are at all points just a passenger. There also the business model changes fundamentally, because in that case you no longer need a driving license and you don't necessarily need to own the car at all. So it's more likely that these will be operated as fleets. At the moment, we as the industry stand right on the verge between level 2 and level 3. So at the moment, we haven't made the jump quite yet. That's because this is actually a really challenging transition. So as I mentioned before, the vehicle also needs to monitor itself, needs to detect failures in its own systems and maintain safety in case such a failure occurs. So we call that property somewhat fail operational, because it needs to continue operating even in case of a failure. This, of course, has quite interesting implications for the system. We also call this property availability. So the system cannot just turn off and hope that the driver can take over immediately, but it needs to remain available. In short, I can summarize this as one statement that it's critical for the vehicle, for the system, the automated driving system, once you go to level 3 or higher, to at the very, very least remain capable of reaching a safe state. What a safe state looks like differs very much depending on the feature you're considering. So here I'm just showing a few examples. This is not standardized, it's just for illustration. So for existing ADAS features, so up to level 2, it's perfectly acceptable for the system in case of a failure and it detects it to just turn off and go silent, because the driver needs to have their eyes somewhat on the road, need to be able to take over basically at a moment's notice. Once you go to level 3, this, of course, if you're watching a video, you need at least 10 seconds, 15 seconds, somewhere in that region, to focus your eyes again on the street, to become aware again of the traffic situation. So you cannot take over immediately. So in that case, the system at the very, very least needs to be able to execute an emergency stop, for example, to brake hard in the lane. For relatively slow features like valet parking, this is of course quite easy to do because in a parking lot coming to a full stop goes very quickly, and also you're not endangering anyone with that. If you're thinking about more advanced features, and I mean the prized one I would say for level 3 is the highway pilot feature, where basically you have automated driving on highways. In that case, coming to an emergency stop is also partially unsafe. So if you do an unnecessary emergency stop in the leftmost lane, of course, there might be faster cars approaching from behind, and you pose, of course, a risk to them as well. Once we also then go beyond that to level 4 systems, where the driver/passenger might also be allowed to go to sleep, this time scale will then, of course, increase much more, and it will become fundamentally unsafe to just stop in your lane. So in that case, you will need more advanced maneuvers or emergency maneuvers that you need to execute. For example, pulling, or most likely pulling over to the right side as a human would and coming to a control stop there. Going even further beyond, once you go to driverless cars, as you would need for robotaxis, you will also most likely need some kind of graded functionality, because otherwise you would always need to wait for a tow truck to come and pick you up. So in that case, you might need to continue at least with lower capability, for example, with lower speed. And if you don't want basically the consumer in the car to notice at all that a failure has occurred, you might need to maintain complete nominal functionality. Now, building these systems is not easy because you need to, at the same time, juggle multiple different criteria. So the main thing that always comes first in automated driving is safety. Safety now is no longer just integrity. So it no longer just consists of writing your your software to good standards, doing lots of qualification testing, tracking your requirements. But now it's also, and you're also using the high integrity hardware like automotive grade controllers. But now it's also an availability topic. So even in case a failure occurs, you still need to maintain some functionality. That priority needs to be juggled somewhat with somewhat opposed one, which is the consumer benefit. So from the consumer's point of view, safety is just par for the course. This is something you need to have, but for the consumer, it's to some extent invisible. For the consumer, what matters is that the system doesn't have a lot of false alarms. So it doesn't do a lot of unnecessary emergency stops, for example. Also, you want the system to drive like a human driver would, to drive at basically a speed that is appropriate for a highway. So not to be super defensive, never do lane changes, and drive very slow. Sorry. The third priority that I also would like to mention is, of course, affordability. So price is always a driving factor in all of this. No, we're dropping out again. Oh, sorry. What is going? Okay. No. I don't. Maybe it's the mouse. No. Okay. Affordability. So you cannot afford to stick tens of thousands of euros of hardware and sensors on a car, because if it gets as expensive as a car with a driver would, then there is no point in having automated cars and automated driving. Okay, so now when it comes to building actual fail operational systems, what do we do? So what we essentially need to do is we need a functionality, and that functionality, even if part of it fails, we still need to maintain some of it. The simple, somewhat naive approach to fixing that is to do redundancy, to basically duplicate the functionality that you need. And then, of course, if one of them fails, you still have the other one. In order to do that properly, you need to consider multiple different aspects. So one thing is, I'm just going to show a few here as examples, the physical location where you put the system in the car. Another one is power supply. You will need redundant power supplies. If your main battery fails, you still need a secondary one. Otherwise, the entire system goes down. You will also need to duplicate the communication network, because if one of them is interrupted, you need something else to fall back on. Another point, I'm going to talk a bit more about that later, is sensors. If a certain area around the vehicle is only covered by one sensor, and that sensor has a failure, you would have a blind spot, and that is, of course, unsafe and not acceptable. And finally, also, you need some redundancy in your actuators. So at least for steering and braking, you need some redundancy. The powertrain is debatable. It depends very much on how complicated these emergency maneuvers that you need to execute need to be. Now, one more challenge that we face in automated driving is once we have the same functionality duplicated, we have two of them, who actually gets to control the car? Who gets to drive? How do we decide which of them does that? Now, in aerospace, what you usually would do is you do something like triple modular redundancy. You have a voting approach. The majority, you do what the majority wants to do. That works quite well in somewhat simple, so not so complex environments. And here we need to keep in mind that the open sky, it's a very empty, very wide environment with not so many traffic participants. On the road, this is no longer true. So on the road, you have lots of other cars that move in quite close proximity to you and are somewhat unpredictable. So here, if you duplicate functionality, both sides might come up with very different solutions to the same problem, and all of these solutions might be correct. So an example shown here is if there is an obstacle on the road, one functionality might say, let's evade to the right. The other one might say, let's evade to the left. Both of them are correct. So both of them are correct, but they do not agree on what to do. So voting is somewhat tricky. Therefore, decomposing a fail operational system into basically something like triple modular redundancy, what's shown here on the left side, with multiple channels, and then you do what the majority wants to do, that's very tricky in automated driving. Instead, a more robust approach is what's shown here on the right side, to decompose a fail operational system into a fail silent system plus a fallback system. Then you have very simple redundancy management logic on top of that, which is that basically if the fail silent system is giving you an output, you take it, you let that control the vehicle. If it is not available, you basically go to the fallback system. That leaves you, of course, with the challenge to build a good fail silent system, but this is, I would say, more graspable because existing level 2 systems, they already fail silent, so we have at least some experience making that. Okay, now another aspect that if you want to make a fail operational system, and now we have redundancy in there, we have the same functionality multiple times, is that you absolutely want to avoid that all of these fail at the same time for the same reason. The obvious approach for that is to ensure that these functionalities are sufficiently diverse, so they are sufficiently independent from each other, and therefore you can conclude that they will not fail for exactly the same reason. The naive approach for making sufficiently independent systems is a black box approach, where you say you make two teams, you put them in separate rooms, you forbid them from talking to each other, and then give them the same requirements and ask them to build independent systems. And hopefully they will come up with completely different solutions to the same problem, which would not fail at the same time for the same reason. Unfortunately, this is, as mentioned before, a bit naive. So the problem is that for some problems, there is only one good solution. Also, even if they're not allowed to talk to each other, it's quite likely that they will have gone to similar universities, will have studied similar textbooks, use the same references online and so on. There is best practices in the industry. So you will somewhere hidden in those black boxes, you will have components that both sides use. You will maybe use the same algorithms or same basic software libraries, and you don't even know about that. And that can, since you're not even tracking that, it can at some point cause a single point failure for both sides at the same time, and you didn't see it coming at all. A better approach is to again make two teams, but now to make it more like a white box, to basically say they still need to build independent systems, but they have to talk a lot to each other. So for every component of the system, they need to hash out, if you use this algorithm, we need to use a different one. If you use this basic software library, we need to use a different one. Here still you will at some point encounter situations where there is only one good solution and both teams want and need to use the same solution. But here at least you are aware of that. You can discuss that, you can track that, and then you can take responsible measures, you can mitigate potential effects of that, you can study potential impacts on the overall system, which of course makes the overall thing much more robust. When it comes to sufficient independence, another aspect that we need to consider is, of course, the sensor set. This is a whole science to itself. I'm just going to touch lightly on this topic. So for the sensor set, what's shown here on the left side of the vehicle, it's something I discussed already a bit before. You need to make sure that all areas around the vehicle are covered by at least two sensors so that it's robust to a random failure of any of these sensors. But more interestingly, on the right side is also that you need to combine multiple sensor types in order to compensate for each other's weaknesses. A simple weather condition that can be quite challenging is, for example, fog. In foggy conditions, the camera and the LiDAR, they will not see very much. They will have very limited range, but radar should be mostly unaffected. So in this case, the radar can compensate for camera's weaknesses. This not only applies to weather conditions, but it can also apply to certain special obstacle types. So if you have an empty soda can on the road, it might give a very large radar cross section. It might appear like a dangerous obstacle that you need to immediately start braking. Whereas the camera and the LiDAR, they will be able to tell you, yeah, this is just a soda can. We can safely drive over it. We don't need to emergency brake now, which of course increases the overall system capability. Now, when it comes to defining sufficiently independent sensor set, there is also many different approaches. So there's no clear-cut solution yet. Some people propose basically splitting sensor sets completely by the sensor type. So basically make one sensor set that only contains cameras and make a different one that only contains everything but cameras. In that case, you can more easily argue that any problem, any issue with cameras is not going to affect the second sensor set. This can be quite challenging, of course, in situations where you have fog, for example, and one sensor type is somewhat limited. Another approach, and this is also driven to some extent by the affordability criterion, is to feed all the sensors you have into the primary system, the one that is doing the actual driving or the consumer features, so the highway pilot, for example. Because usually when you define the overall sensor set that you equip the car with, you want to keep that as small as possible due to cost reasons. They are very expensive. And usually it's designed and tailored somewhat to this main feature that you want to provide. So basically to the highway pilot, you want to give that all the sensor data it needs in order to have sufficient quality. And of course, you need to have a little bit of overhead for safety, but you will usually not add additional completely, well, to the main function, not necessary sensors on top of that. If you then want to define different sensor sets, they will by necessity be more or less a subset of the first one, which means, of course, that there is some overlap. In that case, in order to argue sufficient independence, you usually shift the problem more to the perception side, more to the sensor fusion side, and how you model the environment of the vehicle. So you argue that less on the sensor side. Okay, we'll now move on a bit to the software side, so what you actually need in the software stack. So here I would summarize that the dilemma that you face is mostly performance versus safety. So ASIL here stands for the automotive safety integrity level. So that goes from QM, the lowest one, to ASIL A, and then B, C, and the highest one being ASIL D. For features where people could get, in case of a failure, seriously injured or killed, you usually need to go for the very highest ASIL, so ASIL D. you will have some safety requirements that are ASIL-D in there. Typically in the past, for automotive grade software, what you would use is what I try to very simplified way show here is traditional handwritten software. So with this, you can, of course, since it's handwritten lines of code, you cannot do very complex functionality. So you can do stuff like trajectory planning, but you cannot do advanced stuff like computer vision systems, because there you might need billions and trillions of lines of code that do very complex things like, okay, if these two lines intersect at this angle, then it's a duck, and if it's something else, it's something else. For this is also quite high effort, of course, because it's handwritten code. The good part of that is, because of all the documentation that you do in automotive grade software, is that you can also qualify this code. So you can stamp a high ASIL on top of that. You can reach ASIL-D with software like this. The hardware that you would typically run this on is automotive grade microcontrollers. So they can also reach up to ASIL-D. This hardware is usually not very high in performance, but also not very high in power requirements. So it's quite, it's not very power hungry. Now, if you want to do complex functionality, and in an automated driving stack, you do have some things like that, you will also need something else. I mean, I tried to summarize it here, or simplify it here. So you need some very high capability software that can deal with very complex tasks. That will typically involve machine learning, AI, neural networks, and similar advanced algorithms. So those can cover complex functionality like computer vision systems, and are comparatively to the capability low effort. So you don't have a lot of human written code, because most of the functionality is usually trained from training data. Since it's no longer mostly human written, it gets very tricky to qualify such code, to really be certain that what this system is doing will always work correctly. If you're relying on training data, this can get very tricky. And so far, nobody has worked out a perfect way of qualifying neural network-based code. So it's at the moment not certain that this at any point will be able to reach ASIL-D. Also, the hardware that you would typically use for such complex software is much more powerful and also much more power hungry. So here you will have complex SoCs involving GPUs, involving deep learning accelerators, and also involving very small manufacturing nodes. So you might go down to like 5 nanometer techniques. This, of course, due to power reasons. This, of course, makes it also difficult to qualify such hardware, because you will have inherent limits here. So at the moment, maybe on the hardware side and also on the software side, we can expect up to ASIL-B, which on its own is not sufficient for building ASIL-D or basically the necessary overall systems. So if we now want, in a complex environment like highways, for highway pilot feature, we need, of course, both sides of that. We need some of these green components, we need some of these orange components. Since the orange components are basically a limiting factor for the ASIL that you can achieve, so basically the safety, we need to use some advanced techniques in order to compensate for that. In the ISO, there is luckily something that we can use, which is called ASIL decomposition. So for an ASIL-D safety requirement, you can decompose that, if you find suitable other requirements, into two ASIL-B of D requirements. Those are then in some way complementary to each other, and together ensure that the ASIL-D requirement is maintained. So in our case, if we only have ASIL-B complex software components, we can use something similar. Now we face, of course, a similar problem to what we had before when we decomposed for availability. Now we're decomposing for integrity, more or less. But again, we face the same issue. How do we manage that? On what's shown here on the left side is something similar to these voting approaches. If you use basically 2 times the same component and then you just compare them, so somewhat similar to a lockstep, you run into issues with potential systematic faults in either one of these functions, or in these functions if they are exactly the same, or if they are diverse, you cannot easily compare them. So inexact comparison is also quite challenging. Instead, a more robust approach that's shown here on the right side is what's called the doer-checker approach. In this case, you have one function which is called the doer, so that wants to actually do the actual functionality as best as it can. And then you have a second one, which is called the checker, which receives the same inputs as the doer, but also the outputs of the doer. And its sole mission is to check whether what the doer is proposing is somewhat reasonable or not. So the checker doesn't come up with its own solution, it just checks whether the solution the doer found is acceptable. That, of course, puts a much lower burden on the checker itself. So the algorithms you can use in there are much simpler. A very trivial example here is it's quite difficult to decompose a huge number into two prime factors. So that's a very intense calculation problem. But once you have a suggested solution, it's very easy to check whether this is a correct solution or an acceptable solution or not. So in a way, I mean, I usually use the expression, criticism comes much easier than craftsmanship. Another factor, I mean, I mentioned that multiple times before, we also need to think about cost, of course, when it comes to designing fail operational system architectures. If we go full blast and we want to make a fully redundant and fully diverse system, so we have multiple implementations of the same functionality, each of them on diverse hardware with different hardware vendors, using different operating system, basic software, middleware, and also different algorithms and different application software, we run into a cost nightmare and we run into a complexity nightmare. So this is something we want to avoid. If we now use some of what we've seen before to make this a bit cheaper and a bit more manageable, we can exploit the inherent asymmetry in designing fail operational systems. So not all of these functionality need to do the same thing, and therefore they don't all need to be of the same capability. So of course, for the consumer functionality, for the actual hyperpilot feature, for example, you need to have powerful hardware and powerful algorithms. But for something simpler like the checker channel or the checker I showed you before, we can make do with a lot less. So you can reduce the requirements on the hardware side, but also on the software side. A similar thing also holds for the fallback. So if one of these functionalities only needs to come to controlled stop, so basically it just needs to break and stay between the lines, it can also be a lot simpler. Going even beyond that, we also should keep in mind that the safety parts, so basically the checker and the fallback, those are not directly consumer facing. So the consumer should in the best case never see that. If it's not, therefore it's not a differentiating factor, not a visible one, at least for the consumer. And therefore there is no good reason to compete on that between different OEMs. And if there is no good reason to compete on something, it actually makes much more sense to cooperate on that. So an interesting potential here could be to try to standardize the checker and to try to standardize the fallback. So basically to form some kind of consortium to define exactly what these should do, to define their interfaces, and maybe also to do more, to do comprehensive safety analysis of how to ensure that they are sufficiently independent. In addition to that, some hardware vendors, for example, claim that at some point they will be able to guarantee that there will be no systematic faults in their hardware. In that case, you might also be able to use multiple instances of the same hardware for the different channels you have in here, or lower end versions of the same chip. Similar considerations might also apply for operating systems, for example, or middleware. Okay, if we now combine all of the solution strategies that I've shown you before into a single reference architecture, what we end up with looks somewhat similar to this, which I guess will be familiar to some of you. So essentially, we have a 3-channel architecture. We have a doer, we have a checker, and we have a fallback. Each of these can be ASIL B of D for an overall fail operational ASIL D system. In order to build such a system, of course, we need redundant power supplies, we need redundant communication network, and of course, diverse and redundant sensors and actuators. Important here is, of course, also to align the software between the different channels. We need to consider the entire system holistically. We need to make sure that they will not suffer from systematic faults at the same time. But there is the potential for generic parts to some extent, some system agnostic parts, so the checker and the fallback, they do not necessarily need to be specialized to the OEM. Also potential here is that checker and fallback, those can actually, they should not change too much over time. So you should get them right the first time, and then for the next many years, maybe for the entire lifetime of the vehicle, they will only receive minor updates. Whereas on the doer side, you might need to want to update that every few months to give the consumer more and better functionality. Okay, that already brings me to the last part of my talk. So what we are doing at TTTech Auto in order to help bring this to reality. So one thing that we are looking at in more detail is basically the checker channel. So we are developing something called the Safety Copilot, which consists of a simple, robust sensor fusion solution, and then an extensible framework of validation modules. Each of these can cover one of the complex critical safety goals of the dual channel, so basically to enable this fail-silent ASIL decomposition. And of course, we're also looking into how to manage the redundancy, how to hash out which channel gets to control the vehicle, and how to enable a high availability communication, basically further down the line. And we think that together with a safe execution platform, such as MotionWise, which is our main product, that the Safety Copilot can enable safe fail operational system architectures. Also, as I mentioned before, we firmly believe that cooperation is very important for the industry to move forward. So in the past, or basically in the last few years, we see, of course, multiple different corporations emerging when it comes to safety for automated driving. But most of these only cover certain aspects of safety. So, for example, more on the security side, or more on the testing side. And therefore, in order to bring all of this together to really define one reference solution, we initiated and support the Autonomous, which is a community where we partner with many different OEMs, tier ones, tier twos, and software developers, but also on the legislation side, insurance side, and so on, to really discuss safety in all of its aspects when it comes to automated driving. Here, the main mission is to really cover all the different facets of safety, and then to basically sketch a global safety reference. So basically a blueprint of how we can make an overall safe AD system, which can of course extend then to what should the architecture look like, what should the interfaces look like, how do we do the testing in order to get this basically good for insurance companies, and so on and so forth. Now, as part of the Autonomous, there's multiple events throughout the year. So most of these are hosted virtually. So there's actually one tomorrow. And then next year in March, there will be another in-person event, more high-level event to summarize all of these. So these chapter events are usually on subtopics of the overall thing. If you're interested in joining one of these events or more information, please just go to the homepage at the-autonomous.com. Okay, that already brings me to the takeaways. So as we've seen for level 3 or higher automated driving systems, availability becomes a critical safety property. In order to make a system available, we need to introduce redundancy, and redundancy requires redundancy management. Here, diversity and asymmetry become very beneficial for us. Oh, it's flickering again. A second. Oh, no. Diversity and asymmetry can be very beneficial for us. Demonstrating sufficient independence really requires you to look at the entire system comprehensively, and here openness can be a very big plus that can help everyone in the industry. Because if everyone does their own thing, we might all be stuck with suboptimal solutions. In particular, also, when it comes to safety, this is par for the course. This needs to be anyway, but it's not directly visible to the consumer. And here it might make much more sense to cooperate on something on this instead of competing on it. That might therefore necessitate standardizing architectures, trying to find good solutions together instead of finding them separately. And again, we think that cooperation is that's the essential thing that we need as an industry in order to bring automated driving to the actual road. With this, I want to thank you very much. And if you're interested in something more, please visit also our homepage at ttech-auto.com. Thank you.
All right. Thank you very much. Let's move on to the Q&A session. I think, especially now with the sum up in the end, some of the questions are probably also already being tackled. But nevertheless, let's just hand them over to you. So one of the questions that we got a little bit earlier was, I think, when it comes to the architectural designs, which one do you see the most promising right now, but also going forward? And I have another question that aims in the same direction, which was, what box and sensor set do you see most likely to be the best in regard to cost, accuracy, and safety going forward?
Okay, when it comes to the overall architecture, so we think that a three-channel architecture is most promising. I mean, there's of course also approaches out there where people say we only need two boxes and they check each other. At the moment, we haven't seen any good concept of how this checking each other should work. So usually this, of course, looks very nice on PowerPoint slides, but once you got to actually implementing this, it can get a huge mess. So once you start drawing diagrams, you get lots of arrows that go back and forth and say they need to align, they need to align. So this can be quite tricky. So we think that a simple one where you really exploit the symmetry as far as possible, that this actually can also give us the lowest cost. The boxes you were referring to, I assume refers somewhat to also the sensors. So here we think that for the time being, probably a combination of different sensor types it will be necessary. So some functionality you can only get from cameras, some functionality you more or less only get from radar. I think a big question in the industry was also whether we need LiDAR, whether this will be necessary to bring automated driving to the market, with some very, how to say, high-pitched discussions. So in my personal opinion, long term, I mean, really long term, when it comes to decades, we know that at some point, cameras alone will also be sufficient because that's how human drivers drive. But that requires, of course, very sophisticated computer vision and a very, let's say, detailed understanding of the environment and how environments work. So humans, we don't just do object recognition, we also have a, say, more physical understanding of the environment. We know a lot more about context, and this is something that the moment computer vision systems do not yet fully have. So even if they can beat humans when it comes to object recognition, they don't get like how objects are supposed to move. So I mean, we know, for example, if an object falls down, how it's going to move. So we can somewhat predict that because we have experience on that. And it could be that unless we have artificial intelligence that is at least as good as that, and that would require a lot of understanding outside just the driving realm, that until then, cameras alone will not be sufficient. When it comes to LiDAR, at the moment, I would say it can give you very detailed depth information. And depth information at the moment is, I would say, quite robust because it doesn't require as much artificial intelligence. I've seen also some, how to say, next generation radars where you can also get quite high resolution. So more or less the outputs also look similar to a point cloud. So it could be that this can to some extent also compensate for LiDAR. We will see, but at the moment, LiDAR is used quite sparingly in automated driving systems. So what we see that will actually be available to consumers for the upcoming generations, you will have at most one LiDAR in the vehicle, because on highways, you usually don't need more than that. So you usually have a LiDAR that is facing front. For urban scenarios, it might be different. But here again, on the one hand, the cost per LiDAR sensor is going down with solid state LiDAR. And also, if you're in urban scenarios, this is more going towards the mobility as a service scenario. So this, in that case, cost is a different factor, because as soon as the consumer does no longer own the car, this is basically just, yeah, the cost of running a business. So here, I think from Waymo, there's some calculations where they say if the sensor set and the hardware costs $20,000-$30,000 more, it still doesn't break the business model of them. So here it could be that you might, for the time being, also get additional LiDARs.
I think that's more or less already an answer to another question that we got, which would be, how much do you think are costs for those systems still hindering a faster development / deployment?
It depends to some extent on the level. I would say that, yeah, so for the next generation, this is not something you will see in mid-range cars. So mid-range cars, you will still get the level 2 systems. If you go beyond that, so the level 3 systems that are currently envisioned, that is more the high-end market, so more luxury vehicles. Of course, the expectation is that with every generation that this is going to trickle down further. So on the one hand, of course, you have economies of scale for the sensors, and of course, the software that you already have developed, you can reuse that in subsequent generations. So in particular, level 3, the big investment, the big money factor, this is the first time you implement this. Then the next subsequent generations, you will reuse many parts of that system. So it should hopefully amortize much better. But yeah, so the question is, of course, when we will see the first cars available to consumers that have level 3 or higher. Here, I would say cost, yes, is definitely a factor. And I mean, of course, the automotive industry, there is many challenges out there at the moment. So on the one hand, electrification is a big thing, which of course is competing to some extent with autonomy for the same resources, development resources. And at the moment, of course, with the economic situation, it's also difficult. So yeah, we will see, I would say on that. I'm not sure, I guess there's also some studies on what consumers would be willing to pay for these features. So I guess if you're already investing 50,000 euros for a car, spending a few thousand euros more on basically these advanced features will make sense to people because you can gain quality time. And if you are driving hundreds of kilometers every week, it can give you quite a bit of life quality. So it will definitely be worth it to some people. If you don't drive a lot, having such a feature, well, the question is whether it's worth it to you or not. So until that trickles down to the mid range and then to the low end, will take some time. Yes.
All right, I would say, well, thank you very much.